Hello students, in this video we'll see an example of doing an inverse Laplace transform that results in a Fourier series. Let's find the inverse Laplace transform of hyperbolic tangent of s over s squared. Okay, good. Well, we're going to use the Bromwich integral to do this, right? So in other words, what we're going to say is the following. We have to identify all the poles of this function over here, all the singularities. This function has singularities at s equals 0. And then where's the hyperbolic cosine 0? The hyperbolic cosine 0 where the cosine is 0, because the hyperbolic cosine of I times anything is the cosine of that anything, and the cosine vanishes at the odd multiples of pi over 2, right? And Sn, which is 2n minus 1, I pi over 2, and Sn bar, by the reflection principle, which is going to be a negative 2n minus 1 I pi over 2, where n goes from 1 to all the way up to infinity. Good. So now I have to compute all the residues of the function what? So therefore, hence, the inverse Laplace transform of hyperbolic tank of s over s squared is going to be, let's call this function over here, let's call this f of s, right, is going to be f, the residue of f of s e to the st at s equals 0, plus the sum of all these residues over here, plus twice the sum, n equals 1 to infinity, the residue of fs s to the t at s equals sn, plus the residue f s st s equals sn complex conjugate. Now remember, we have a formula for how we handle these things with conjugates, right? So the formula we have is the following. So the residue of f of s e to the st at s equals sn, plus the residue of f of s e to the st at s equals s and conjugate is going to be twice the real part. Now these are purely imaginary, right? So there's no coefficient of e to the alpha t over here. Twice the real part of e to the I, and then I'm going to have an n, 2n minus 1 over 2, 2 minus 1 over 2 t, right? And then times the coefficients over here and the expansions over here, times the coefficient, times b1, I'll say b1n, or what is b1n? b1n, and I'll show these are all simple poles, right, since where f of s is equal to b1n over s minus sn plus the holomorphic part, right? Holomorphic part. How do I know these are simple poles over here when n is equal to 1? Because the cosine over here has a simple pole at that number over there. So I'm using the fact that cosine is a simple pole, so there's only one term we have to consider over here, right? So I need to find these numbers over here, b1n, and I have to sum these things up over there. Great, so how are we going to find those numbers? So we have two residues to compute. We have to compute, first of all, the residue at 0, then we have to compute the residue at these numbers b1n, okay? So note, recall, that the hyperbolic tank function is equal to s plus some number, which I can never remember, it's usually like 1/3 probably, some number c1 s cubed near the origin. Okay, that's the Taylor expansion because it's analytic near the origin, tank is, right? And so therefore, if I hit it with 1 over s squared, then this implies therefore that tank of s over s squared looks like what near the origin? Looks like a 1 over s plus c1s, etc. And therefore I can find the residue, right? The residue of tank of s times e to the what? Times e to the st at s equals 0. Well, s equals 0 over here, I'm just going to do what? I'm just going to say it's going to be this residue over here times e to the 0t, just a 1. And so hence the residue, this implies that the residue of f of s e to the st at s equals 0 is just going to be equal to 1. Beautiful. The first term in the series is 1, okay? Now, since they're all simple poles, how can I compute these things over here? So note that our function over here, that tank s over s squared is really what? Is really sinh of s over s squared cosh of s, okay? And this has the form P over Q, and at simple poles we know how to compute residues, right? So in other words, the residue of this function without the exponential, I've incorporated the exponential into there, these numbers b1n, okay, that's just that corresponds to the f portion of these things, right? So I just define the f portion of those guys. So what will this be? So the residue of sinh s over s squared cosh s at s equals Sn are just those numbers b1, n that we're discussing. Excellent. Okay, good. And so how are we going to do that over there? Well, with a simple pole, you're just going to plug in the sinh of Sn and then the derivative of this thing. So what's that going to be equal to? Those residues are just going to be the sinh of Sn over the derivative of this thing is going to be 2Sn cosh Sn, those are gone, plus Sn squared sinh Sn, like that. Great, okay. Excellent. And so what's going to happen over here now? So what's the sinh of these numbers over here? Well, I have sinh on top and the bottom over here, so those numbers are just going to cancel out, right? And then we're going to have the real part of this thing over here. Good. And so let's see what we have going on. So do we have any calculational errors? I don't think so. I think that's going to be good. These numbers over here are gone, right? And then these numbers over here, derivative of cosh is going to be sinh. So I just plug in those things, and what will I get? So the sinh are going to cancel out. I just get 1 over Sn. 1 over Sn squared, right? Which is going to be what? Which 1 over Sn squared is going to be, so because of course the sinh just cancel out, and the cosh of these numbers is going to be equal to 0. Good. Okay, and so that's going to be what? That's going to be a pi squared over 4. So that's, I'm going to flip everything, so it's going to be a 4 over pi squared. Everything flips. There's going to be a negative sign, right, because I squared. And then I'm going to have to flip, the 4 everything goes on top, and I have a 1 over 2n minus 1 squared like that. Great. Now we're done. So therefore, what's the inverse Laplace transform of this thing? So this implies that f of t, the function itself, our inverse Laplace transform, so the inverse Laplace transform of f of s as a function of t is therefore the residue at 0, which is 1. And then I'm going to use this formula over here. Well, what's the real part? These numbers over here are real numbers over here, so I can pull those out. So minus the sum, n goes from 1 to infinity of, and I have 2 of them, so I'm going to have an 8 over pi squared, 8 over pi squared. And then I'm going to have a 1 over 2n minus 1 squared. And then lastly, I have to do what? The real part of this thing over here is going to be the cosine, right? So then I'm going to have the cosine of 2n minus 1 over 2t, like that. Therefore, the inverse Laplace transform of this function over here, this hyperbolic tangent over s squared, is a genuine Fourier series. It's a genuine Fourier cosine series. So what this tells me is that these inverse transforms are intimately connected with the theory of PDEs, because these things pop up all the time when you're solving different PDEs, right? Like namely the Laplace equation. And so now we have access to understanding transformation methods. So this allows me to do this bridges the gap between the discrete series and integral transformation methods that we'll discuss when we start solving PDEs on finite domains. And so right now the Fourier expansions of those solutions of those PDEs, and we'll see how these initial conditions, these initial data pop up in the context of taking the Laplace transform. Thank you very much.